Hello everyone, my name is Han and welcome to my channel. Today we continue our crypto series. We left off on finite sets, which are basically sets of a finite number of elements. And we're going to extend with finite fields. So when you have a finite set, whether it's a set of any kind of elements, we know that there's a one-to-one mapping with a set of integers from 0 to n-1, n being the number of elements in the set. A finite set of integers is much more convenient than regular finite set because you have a set of operations. You can do multiplications, you can do additions, and in general there are many more studies in a set of integers than in the regular finite sets. So from now on, we will only be interested in the sets of integers from 0 to n-1. And we're going to call it np, well, from 0 to p-1. In fact, in this set, we can use the classic addition and multiplication. And the only difference between the regular addition and multiplication in a set of integers is that since the result cannot exceed p, the number of elements in the set, we are going to subtract the multiple of p until it does. So, for example, if p equals 60, which is what we use for hours or minutes, 60 minutes in an hour and 60 seconds in a minute, we can do 10 plus 20 equals 30. But if we do 45 plus 15, the result is 60, which is equal to the p60. Therefore, it wraps around to 0. And if you do 45 plus 30, then now the result is 75. And we wrap around to 15. So anytime you go above 60 or below 0, you wrap around either on the positive side or on the negative side. Multiplications works exactly the same way. So if you do 5 times 10, you get 50, which is still below 60 in the range 0 to 59. If you do if you do 10 times 20, then you get 200, which is clearly above 60. Which is even above 60 if you subtract 60, because if you do 200 minus 60, you are at 140. So you have to subtract even another 60. So now you are at 80, which is still above 60. So a third time you subtract 60. And finally you get 20. So this is called arithmetic modulo something. So modulo 60 in our case. And you can also say right away that 10 times 20 equals 20 because it's equal 180 plus 20, where 180 equals 60 times 3. So whenever you eliminate every multiple of 60, you're fine, or any multiple of p. If you take np plus with the plus operator, you get a couple pair, np and plus, which forms an algebraic group, which is called an algebraic group. Because plus has a set of properties, it has a neutral element, 0, the same neutral element that you have in the addition. But plus is associative. If you do a plus b plus c, it's the same as a plus b plus c. And if you have an element a, then you have an opposite. So you can find an element, we call it minus a, such as a plus minus a is equal minus a plus a is equal to 0. These properties mostly come from the addition, and they are not very difficult to prove on the set NP. The only thing that we have to be careful about is the fact that plus has to be stable in regards to NP. In other words, if you have two elements of NP and you do plus on them, the result stays in the NP, which is obviously the case here. If in addition to this, these properties, you also have the fact that a plus b equals b plus a, then we say that the group is commutative. So NP with plus is a commutative group because plus is also commutative. That's not always the case. There are some operators that are not commutative. So, for example, the matrix multiplication is not commutative. if you do A times B, it's not the same as B times A. Once you have a group, you may also be interested in the subgroups of this group. Basically, the subgroups are sub-elements of the group, which relative to the same law, same operator, also form a group. So, for example, if we take our group N60 and with the addition modulo 60, can we find a subgroup of that group? And the answer is yes, because if you take the elements 0, 10, 20, 30, 40, 50, basically elements separated by 10, then you can see that if you add two elements of this subset, then you will also fall under the same set. So, for example, if you do 10 plus 20, you get 30. If you do 30 plus 30, you get 0, because you wrap around 60. And anytime you add two elements of this subset, you still remain on the same subset. And also the properties that plus has remain valid in a subset. So you also have several other subgroups of N60. And in fact, if you have any divisor of 60, you can see that the set will also be a subgroup. So if you take divisors of 60 are 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. You can look at on the clock, and you can see that if you increment by steps of 2, for example, you will fall exactly, you will wrap at 60 after 30 steps. And with all the numbers that are given, you would take an even number of steps to go exactly over 60. So they all form a subgroup. So far, we have the set, so NP, and we have one law, and we have put some conditions, some properties on the law in order to have some better structure. We're talking about group and commutative group. Now we're going to add one more operator. So we're going to add the operator called multiplication. And again, that operator has to obey a certain set of properties so that the result is a mathematical construct that is going to be very interesting for us. So we take NP, we have plus. This time plus, we want it to be forming a commutative group. So before it was just a group, but in fact plus was commutative. And we also want multiplication, multiply, times, to be a commutative group. So we have, let's summarize, we have NP plus a commutative group with neutral element 0, and we have NP multiply with a commutative group as well, but this time with neutral element 1. Right? So we're saying that any element A times 1 is equal 1 times A is equal A, and A plus 0 is equal 0 plus A equals 0, and the other rows are also correct. So associativity and inverse element. And the new thing that we want this time is some relation. Otherwise, plus and multiply would be completely unrelated. So we want something that combines plus and multiply, and it is the distribution of multiplication over addition. And again, that's very common. I mean, that's very intuitive. We are saying that A plus B times C is equal to A times C plus B times C. So stuff that you have learned since primary school. So we can take a look at NP plus multiply, this triple, and we see if all these things are valid. And if they are all valid, then we have what's called a field. So for the case of NP, everything seems to be okay, but we have to be mindful of one thing, is that the inverse for the multiplication has to remain in the group or in the set. So, yes, because NP multiply has to be a commutative group, and a group at very least. So the problem here is that if you have an integer and you want an inverse, the way we define inverse usually is to use the inverse of real numbers. So for example, if we have 5, the inverse of 5 is 1 over 5, which is 0.2. And clearly, 0.2 is not an integer. So we're looking actually for a number, an integer, such as that integer times 5 is equal to 1 modulo p. So that's the definition of an inverse. So the inverse has to be an element of the group, or the set, sorry, such as if you multiply that by the number, the original number, you get the neutral element. And here you get a neutral element modulo 60. In other words, by a multiple of 60. And if you want a field, every element of the field of the set has to have an inverse. It's not like some elements have an inverse. You always know that 1 has an inverse because 1 times 1 is equal to 1. But the question is every element of the group with an inverse? Except for 0, I forgot to mention that, but the element 0 does not have to have an inverse, should not have an inverse. And one of the interesting results is that if p is a prime number, and actually more generally, if p is a power of a prime number, then NP is a field. And in which case, we generally speaking, we don't write NP, we use FP to remember that FP is a field. And in cryptography, we always use P as a prime number of a very large value. For Bitcoin, P is around 2 power 256. So the exact number is on the slide. And this is a really, really, really large number. You can see all the digits. And your private key is going to be somewhere in that range. So unless you have a very broken random number geometer, the odds that two people have the same secret key are astronomically small. So basically the chance is that you get the same account that somebody else are negligible. This is all we need to know about finite fields for the moment. It's not much, but they are going to be used everywhere. So this is something that we have to be familiar with.